Good morning, all of you. It is a great pleasure for me to announce that Laurent Demonet will be beginning his lectures today.
Okay, so thank you very much, Ashish, for the introduction and for the invitation as well. So, yeah, I will very briefly explain what is the global aim of this lecture series. So, several speakers introduced or used cluster algebra already. So, let me just make a kind of diagram here. So, on one side, I will put cluster algebras. And, okay, you need a certain number of tools to define a cluster algebra. So let's say a quiver. It could be a matrix. I don't really mind. I will not enter too much. I mean, I will not detail that today. So let's say a quiver plus some rule to do, plus some cluster variables, plus some mutation. So you have some family of some combinatorial tools which permit you to generate cluster variables. So it's a very elementary definition somehow. And some properties can be proven directly. If you try to prove some properties, it can, but very fast you face a problem. The problem is the following one, is that this definition is inductive. So if your property is something which can be moved along the exchange diagram, this is relatively easy. However, very often, you need to start to have a global view on the cluster algebra. And this is much more difficult because it's very difficult to control this induction. I mean, it's not an easy problem. One possible solution is called categorification. And this is a very vague term. It has several meanings. So what I call categorification is sometimes now called additive categorification. So I will speak about additive categorification. So what is the idea? The idea is to find this as a shadow of some more elaborated structure. So you have several choices, which are all categories. You could take a representation of quiver, for example. So this is what I will explain. You can do some other things. So there are other choices, more, or more, how should I say, more elaborated choices. And okay, you will have to wait for next week to know about them. There will be a talk by Bernard, and a series of talks by Bernard, and a series of talks by Pierre-Guy Plamondon. And they will explain other possibilities. But you need to understand this one first, as it's the most elementary possibility. So I will try to explain that. And essentially, the link is the following one, is that you will associate two representations. So I don't say how like that, some cluster variable. And for that, you need something which is called, okay, originally Caldero Chapoton map, sometimes cluster character. So I will call it TC as a common possible choice that I don't need to choose. Okay, so it's cluster character or Caldero Chapoton map. And what does it use? It uses two tools mainly. It uses something called Auslander-Reiten theory, plus some geometry. So today I will focus on explaining representation theory of quiver. Tomorrow I will focus on explaining AR theory. And next week, So I will have 2 lectures more. I will explain the Caldero-Chapoton map and the geometry you need. I mean, and probably in between we will agree with Pierre-Guy and Bernard to do something coherent, not to repeat too much on our talk. Anyway, I start by representations of quiver. So I will give you a definition. So representation of quiver. So I take a quiver, I take the same notation as Jacob took. At this point, I don't do any assumption on my quiver. I might do later, but now I don't need anything. So I take a quiver, a field. The same, I don't do any assumption at this point. At some point, I will assume that it's C, but I can do it much more generally at this level. And the definition, so a representation of Q. So maybe I call it X, a representation F of X of Q. It's a very easy datum. That is, so first a family of vector spaces. Okay, I will never repeat K. K is a field which is fixed one time for all. So vector space means K vector space. A family of vector spaces that I will denote like that, xi for I in Q0, so indexed by the vertices, and a family of linear map. Which in turn are indexed by the arrows and which work as they should work. So they go, if you have a certain arrow Q, you take a linear map from the starting point of Q to the ending point of Q, and I will call it XQ. It's a bit arbitrary. Some other people have other convention. Okay, so it's a very simple object. You can see it as some kind of diagram. You put vector spaces on vertices and you choose a linear map in between. So of course, it's not enough to study them. I mean, we need some more structure, and what we will define morphism. So a morphism from a representation X to a representation Y is just a family Fi. So Fi goes from Xi to Yi, indexed by the vertices of your quiver, with the natural compatibility condition with the arrows, such that the following hold, such that for all arrow, you have a commutative diagram. That means that if you start from the starting point of the arrow, you have this thing which goes to the ending point of the arrow. Then you have your map, your morphism, which goes here to YSQ. Then here you can, of course, do the same because you have another representation. Then you go Q, and here you have F at index T of Q, and you require that it commutes. And for those who are not used to diagrammatic notation, it just means that the composition like that is equal to the composition like that. So when I say that a diagram commutes, it essentially means that each time you have two passes between two vertices, the morphisms they represent are equal. Well, that's all. So this is for one notion. Okay, and I will maybe introduce two notations. Home from X to Y is just it's just the set of morphism from X to Y. Okay, morphism. So I'm sorry, the notation more have been introduced before, but we are really used to home in this field, so I will use home. Otherwise, we will get confused or, yeah. Okay, and then another notation, I will write and x equal home xx, which is not completely accurate because okay, this is a k-vector space, right? You all agree? This is a vector space. This is, of course, also a vector space, but it has more structure. That's why we take a special notation. It's a so-called k-algebra. So it just means a k-vector space with a composition, with a multiplication, but which here is just a composition, because the composition of morphism give morphism. Okay, and last in this definition, I will tell you, I mean, you all know that, but I just remind, we say that F is an isomorphism if there exists some F minus 1 going in the other direction, such that F minus 1 is the identity morphism of, so F minus 1, it should go from probably Y, yeah, and F minus 1, F is just the identity of X. So I didn't say what is the identity, but it's pretty straightforward. You put the identity everywhere. I mean, yeah, for each object, you have an identity map, and it behaves well with the composition, obviously. Okay, so now I have some objects and some morphisms, so I have a category, even if I didn't redefine what it is. We have a category, we have a notion of composition. Notice that I have a bit more property, so this is what I will say now, or maybe I do an example before saying that. Maybe an example that you can check by yourself. I will not help you too much about that. I take this quiver, and then I could take, for example, X, this representation. So I go from k squared to k cubed. Why not? I put this matrix. Then I take Y from k squared to k. I put which matrix I did put? I put 1, like that. And then I can decide that, for example, F1 is equal to, I decided, I copy because I don't want to have to check the commutativity relation. Okay. So, yeah, this is an example. Please check if you are not sure. The only thing to check is that this commute. So just multiply two matrices and check. Okay. Okay, so this form a category, and more precisely, so it will be, I called it proposition. Representation. Oh, by the way, I know that it's very elementary, but for specialists, please check if there are mistakes and tell me that. And for non-specialists as well, actually. Representation of Q form a so-called K-linear abelian category. So what does it mean? I will list the properties that I want. So first of all, first property that I want, home XY. Sorry, I'm very, I'm not so serious about quantification, so I never say let x, y in, okay. So when I say om x, y, it means for all x of y. Yeah? Om x, y is a K vector space, and the composition is bilinear. The composition between any two of these things when that can be composed is bilinear. So this is the first thing we want. There exists something called a zero object. So just to simplify at this point, I will just say that it's an object which has zero endomorphism ring. And this is enough to characterize it. There exist direct sums. So what does it mean? Okay, I don't want to do too much categorical language, but you saw in some talk the notion of limits, and there are plenty of things that you can define as limit of very particular system. So this is somehow one of the most easy possible. So direct sum exists, and I will not tell in detail, but they behave as you expect them to behave, essentially. Two, so I put all this one in one. There exists kernels. So what is a kernel? Maybe I remind in a few seconds what is a kernel, because I want to avoid some ambiguity, actually. So what is a kernel? If you have a morphism F, a kernel of F is a map from somewhere to X. So it's a map like that, so which comes from somewhere. I will call it K for now, such that for all, so maybe I will change map, for all map from, say, okay, let's say K prime to X, satisfying that the composition here is 0, there exists, maybe I should just write like that, there exists some factorization here. So when I write some diagram like that, I assume that everything commutes. So what I mean is that each time you have a map from a certain K prime to X such that the composition of these two maps is 0, then you can find another map from K prime to K such that the composition here is equal to your original map. And moreover, it is unique. Okay, this is the definition. Yeah? So, sorry. Yeah. I will explain it in 1 second. I finish my proposition and I tell you on this example. Actually, I will let it as an exercise and I will give you some hint to prove it. So normally you should succeed. So you have a notion of kernel, and what do I want to emphasize is that most of the time, if you did linear algebra, what you call the kernel is K. But what I want to call the kernel actually is the map. But as I'm not so rigorous, sometimes I will still call K the kernel. So remember that the kernel can be either a linear map or the domain of this linear map, depending on the context. 3, there exists co-kernel, and I will not show you, but essentially you take the same diagram and you reverse all the arrows. So this is a dual notion. And 4, something slightly more complicated, so I will maybe write it here. 4, if you have a map F, now that you have the previous tool, you can do something. You can take the kernel of F. So I have the kernel of F. Oh, by the way, I didn't say something. There exists kernel, but actually you can prove that they are necessarily unique. So maybe I should say like that, but this is not really a part of the axiom. It's just a consequence of the definition. So just to make clear that when I say that, I'm really speaking about something very specific. And then you can take the co-kernel, which is of course here, even if I didn't write it explicitly, and I will call it like co-kernel, it's maybe not so good. And of course now you can continue to play, you can take the co-kernel of the kernel. So this is the co-kernel of the kernel. It's a bit Yeah? And actually, this thing, you will call it co-image. I will tell you in 1 second why we call it co-image of F. And then, in the same way, you can take something here, which is the kernel of the co-kernel, and you call it the image. So pay attention once again. Now I'm being a bit sloppy. Image might be also, I mean, image is really the inclusion inside this thing. So you have the image, and the fourth thing that I want is that, so the important part is that there is an isomorphism here which makes that commute. So the axiom, maybe I should say it, the axiom is really the existence of this isomorphism here. Therefore, we never speak about co-image because we identify the co-image with the image. That's why you never hear about co-image, okay? So just think about the image, but the image has two canonical realizations. This is what you call in linear algebra, I think, the first isomorphism theorem, if I remember correctly, which tells you that the image, which is a subspace of the range of the function, the codomain, is isomorphic to the domain modded out by the kernel. Okay? But for abelian category is an axiom. And proof, please do it by yourself. It's not difficult. If you have difficulties, it's because you did not understand correctly the categorical notion. So open a book about categories if you have difficulties to prove it. Yeah? No. Okay. I will do a slight part of the exercise. This map always exists and is unique by definition. Why that? So I can try to play with diagrams. It's actually a good exercise. What do I want to do? I want to find a map here which makes F being equal to this composition of three things. So how would I do that? I will try first to factor F through that. But you know that the kernel of this composition is 0. And when the composition is 0, F factor uniquely through the co-kernel of the kernel. This is the definition of a co-kernel. And then you do once again the same story here. So the uniqueness comes from the uniqueness of kernel, not the uniqueness of kernel and co-kernel, the uniqueness here. This arrow is actually obtained just by applying twice, not twice, by applying once this one and once that one. So you have the arrow. The point is that if you take a random category with kernel and co-kernel, usually it's not an isomorphism. The actual content of the axiom is that this arrow, which always exists, is an isomorphism. Okay? So you need it to be an isomorphism. So this is maybe slightly more tricky to prove than the other one. The other one are relatively easy. And why they're easy in this context? Because now you can think that all these constructions are made vertex-wise. So the kernel, you take the kernel of each F, and then you can prove very easily that you can restrict the map corresponding to the arrows of your presentation to the kernel. So it's relatively easy. Just do it vertex-wise, okay? Okay. And this is the same for the direct sum. And for the direct sum, you take direct sum vertex-wise, and then you have diagonal matrices somehow. Okay. Now that I said that, what did I want to say now? Oh yeah, I want to introduce another definition, which would actually be what I will be interested in. I realize that I didn't give name here. So it's an abelian category that I will call rep KQ. And sometime or often I will forget the K. And rep KQ with a small k is just, so it's not, yeah, okay. What I will write is not the universal definition. I'm sorry, it's a bit specific. These are all the representation of Q satisfying that for all vertex, the dimension of the space at this vertex is finite. So here I don't make any assumption. I can define everything without assumption. But now I want to consider finite dimensional representation. And in such a case, I call dimension vector of, so, and we write like that, the dimension vector of a representation. So X is a representation as usual. This is just the vector consisting of all dimension of the xi for I in Q0. So this is a vector. I don't order necessarily my vertices, but take it as an abstract vector. Okay? So this is called the dimension vector. And sometimes when we speak about the dimension of the representation, we just sum up all this dimension. But at this point, I'm more interested in the dimension vector. So, okay, we have that. And I need some other definition. So there will be a lot of definition and a lot of exercise in this lecture because most of the propositions I will give are really straightforward to prove as long as you understand the concept. So try. If you are not used, try. And if you don't understand the concept, see it. And if you understand the concept, you will see it as well. So we say that an object X is indecomposable. Two things hold. First of all, X is not the zero object. So I did not introduce this symbol. It means isomorphic too. So isomorphic means there exists an isomorphism in between. Okay. Sorry. When I say that, yeah, you could say equal for zero. I can explain more if you want, but yeah, I put either not isomorphic, but it does not really matter. But in the second case, it matters. Whenever X is written as X1 direct sum X2, then one of X1 or X2 is isomorphic to 0. Okay, yeah. I don't know if I replied to your question. I told you that you can construct the kernel vertex Y, so that means the kernel here, you just compute the kernel of F1 and the kernel of F2. Okay, just to answer the question, which, okay, so this is the definition of an indecomposable object, and they will play a big role. And my aim is to do as fast as possible the link with cluster algebra. So now I will also define that Q is of finite representation type if rep, so once again, now I'm interested in finite dimensional one, as finitely many isomorphism class, so sometimes we say isoclasses, of indecomposable object. Okay, so maybe, okay, this rep always means representation. Maybe some comments about this definition. I speak about isoclasses. And otherwise, this would not even be well defined. The point is that when you are doing category theory, you somehow consider that things that are isomorphic are actually the same. It's not completely true, but if you want to count something, you will always count up to isomorphism. This does not make sense to try to count things without modding out the isomorphism. So, yeah, you take isomorphism classes. And why I say that it will permit me to make a link with cluster algebra, I will let you guess the link from the proposition I will do, which is not an exercise because it's too difficult, and which is not proven either because it's too difficult as well. So theorem, which is called Gabziel theorem, Q is finite representation type if and only if Q is Dynkin of type ADE. Oh, okay, of type ADE, it's not very important because if you remember correctly, they are the only type which are simply less. So otherwise, you don't have per se a quiver. You could generalize, but I will not do it. And if you have questions at some point, I can tell you, but not now. So we have that. So it looks pretty much like the theorem cited by Jacob the other day, but it will look even more in 5 seconds. You also have the following thing. In this case, there is a bijection between indecomposable modules. Okay, I will write it like that. I will write index Q, but you understand what I mean. Modulo isomorphism to the positive root. So you remember what are positive roots. Don't remember, please review Jacob's lecture, of the same type. And actually, it's pretty easy to describe this bijection. So I will write it like that, because I just already defined the bijection. So if you take the dimension vector, it's naturally something which is a vector indexed by the vertices of the quiver. Okay? So it's the dimension arrive in, so the positive root are in, so I will write it like that, but of course they are with positive coefficient actually. They are in V to the Q0. And of course, in the case of, in the talk of Jacob, the vertices were numbered, and then there was a natural bijection between Q0 and some initial segment of N. But yeah, for some reason, I don't want to bother to number quiver vertices at this point. So it's just like positive roots in V to the Q0. Okay, so it's almost the same theorem, except remember that there were the negative simple roots that we don't catch here because the dimension cannot be negative, obviously. Okay, so this theorem, I will not prove it. I can maybe give a hint of the proof. It's not a hint because I don't expect you to be able to prove it with my hint, but main tool maybe of the proof is called reflection functor. And what does a reflection functor do? A reflection functor somehow associate to some representation of Q, a representation of the mutated of Q. So we'll not enter much more in detail, but you can do that, and it acts on the dimension as the reflection that Jacob introduced. So you have a perfect correspondence, and by playing with this reflection functor, you succeed actually to prove this theorem. But it takes several pages, it's not a trivial thing. Okay. So you have reflection functors which permit you to prove that if you spend the time you need. Okay. Now, another definition I need, sorry, there are plenty of definitions. A short exact sequence, so probably some of you, most of you know already, I'm sorry. A short exact sequence. So what is a short exact sequence? Is a pair of morphisms of the following form, and so that I will write like that. I'm sorry, it sounds not like a pair of morphisms, but what I want is really a pair of morphisms which are appearing here. Obviously, when I say morphism, the data of a morphism include the domain and the codomain, otherwise I'm not such a thing as a morphism. So that F is the kernel of G, and G is the co-kernel of F. So I don't know if it's exactly the definition you know usually, for those who, I don't know, who know in other contexts, but think of it element-wise is exactly what you want. So a kernel is always injective, I didn't prove it, always monomorphism, also what we said, it's always injective, I didn't prove it, but it's not difficult, it comes from the uniqueness here. You can prove it easily, so it's always injective. A co-kernel is always surjective, and what says exactness at this point? It says that if you take something here and you map it to 0 here, then it comes from here. And yeah, it's exactly the fact that F is a kernel of that. And conversely, I mean, yeah, conversely, you can work it out by yourself. If you know an element-wise definition of short exact sequence, you can work it out. That is actually what you should do. Okay, so maybe a comment about this definition, maybe you noticed something, is that as much as possible, I give definitions which are independent of quiver. So my definition here would be true in any abelian category. I mean, you don't need a quiver to make this definition. You need kernel and co-kernel, that's all. Okay, you don't need, and you actually need less, but I don't want to state more about that. So all what I say, when it's stated in categorical language, you can extend it to any abelian category you know or you want to know. Okay. Okay, so I have short exact sequence. And we say the sequence are equivalent, we'll call it psi. We say that psi is equivalent to psi prime. So I will not write psi prime now, but it's another short exact sequence. If there exists a commutative diagram of the following form. So I write psi. So psi is my first short exact sequence. I write psi prime, which is my second short exact sequence, but I require that it starts from the same x. Y, I don't care, but it ends at the same v. And now I have some morphism which always exists that I write equal. So pay attention in a commutative diagram when I write an equal, it means identity. But we are used to write equal when we want to write identity. Something that I don't require anything a priori, some psi, and some equal. If these three things exist, then we call these two sequences equivalent. And notice that, maybe as an exercise again, sorry, I put a lot of exercise, it implies automatically that psi is an isomorphism. Okay, so actually psi is an isomorphism, but you don't need to require it. It's implied by the diagram. Another remark, you cannot replace these two things by isomorphism. Okay, but I will not tell it too much, but yeah, this is really equality. And then now I define an extension from V. So it will make sense for those who are used already, it will make sense soon, I guess. An extension from V to X is an equivalence class of short exact sequence of the form 0, X, Y, V. So when you speak about extension, essentially you fix the two terms and you allow to choose any Y which can fit here and the short exact sequence. But you consider it up to this equivalence relation. And then you can consider the set of all extensions. So what I will do, x1 of Vx is equal to the set of extensions. Okay. From V to Y, from V to X, sorry. Okay, you will discover later why it's from V to X and not from X to V. I don't have a good argument at this point. So at this point, it's just like that. I call that from V to X and not from X to V. But yeah, that's fine. You can just you can just think of it like that. Maybe I give an example. Or an exercise example at the same time. So I give an example, and the exercise is to check that I didn't do any mistake in my example. So suppose that I still take the same quiver, and I claim that there are short exact sequences of the following shape. So you can construct short exact sequence of the form 0k. I put the arrow, but of course it's 0. To kk, I can put any lambda here, and to k0. Okay. I create a short exact sequence like that, and here I will write a bit more specifically my morphism. So, okay, I should map k here, and the only way I have to map it is to put it on the second vertex, because it should be compatible with the vertex, but I just put the identity, right? And here I do the same. I put the identity 0. Okay, you see what I'm doing. And it will work for any lambda. You can do that for any lambda. It's a short exact sequence. But the point is that actually it implies that x1 of k0, 0k, and I will say with quotation mark at this point, it's just k. So at this point, it's a weak statement. I'm just saying that each different lambda gives it different extension. Please check that it fits. Pay attention, you really need equality to get that. Okay, so now the next thing I want to do is to remove the quotation mark around the equality, so to make more sense of this equality, actually. But before, I want to do some kind of construction. I need to probably accelerate a bit, but I guess it's okay. I want to do a construction, so which will be called a definition proposition, maybe / exercise, because I will not prove the proposition, but you are all able to prove it. If I take psi a short exact sequence, I can construct the following commutative diagram, and which direction I wanted to do first. Does not really matter, and f a map from a certain z prime to z, I can construct a diagram of the following form. There exists a commutative diagram of the following form, and I would be tempted to say unique, but I don't want to tell exactly in which sense it's unique, so I put it in parentheses. So what's the diagram I want? I want a diagram of this following shape. So I have this already, then I have a f which go like that, and then I want something which look like that. Okay, so maybe I will call that u and v, that u prime and v prime. So, okay. The thing which are fixed at the beginning is this and that, and the existence tells you about that, and tells you also that this is a short exact sequence. So yeah, maybe this is psi, and this is, okay, I will give the notation after, but it's implied that this is a short exact sequence. Maybe I write it, but when I write something which looks like a short exact sequence, it is a short exact sequence, otherwise I don't do that. Okay, so there exists a short exact sequence and such a commutative diagram. And the hint to prove it, that is to say that y prime is the kernel of fv. And if I want to be even more precise, I will not say that y prime, because y prime is a space, but I want a kernel, so a map. I will tell you that so v prime minus f prime is actually the kernel of fv. And now I realize that I didn't say something, so I will say something. When you have a direct sum and you take map morphism between two direct sums, you can always write it as a matrix. So when I write this thing, fv, what is fv? Fv is a map from z prime plus y to z. Please check that you can actually write maps from this to this as one map from this to this and one map from this to this, and that it makes sense to make this as matrices because you compose them as you multiply matrices. So that's the reason I write them as matrices. You compose them as matrices, as multiplication of matrices. Okay? So we have that, and don't hesitate to ask questions. I mean, I don't know if I don't do posts to ask you to ask questions. But of what? Right, the definition, okay, yeah, you are right. I didn't finish the definition exercise, but one first definition is that I will write that psi composed with f. Okay, it's a notation than a definition, and I will explain you you will understand why this notation makes sense very soon. The first thing you can see that I have an extension from z to x, and when I compose with a morphism from z prime to z, I obtain an extension from z prime to x. So it kind of makes sense as you are used to compose a map. Yeah, if extensions are the kind of higher level version of maps of morphism, then it makes kind of sense to use this notation. It's more notation than definition. And okay, it's more notation than definition actually. Should maybe call it notation. And then you can do the dual. So dually, if you have a map that I will call, I don't know, maybe J, from x prime to x. No, not from x prime to x, from x to x prime. You can do the following thing. I just write the thing. So you have x, y, z, your original sequence, that I call it psi. And then I have a map from x to x prime. And here I go to y prime. Here I put z, an equal sign, 0, a map here. Here, of course, it's g. Here it's 0. And this you call it, as you can imagine, so J composed with psi. Yeah? I didn't say anything about extension. For now, extension is a set, and it will become something else very soon. So please wait. Now I'm speaking of sets, and I'm doing formal things with sets. Okay. So, right. Another way to say that is a very good question, but normally it would be answered very soon. So anyway, I have this thing, and in other terms, I could write the composition. I mean, I define plenty of composition with the same symbol, but normally it should be easy by the context to know what I mean. So the first one, it goes from x1 of x of vx cross home v prime v to, so this is always the annoyance about composition, but you should notice that it works as a composition of morphism, v prime to x, and the second one goes from home x x prime cross x1 vx to x1 Vx prime. Okay, so this is just a reformulation, but you have these two things which, okay, now there is no more structure. You could ask me, oh, did you say that it's bilinear? No, not yet, because I have a set. I don't have a vector space. Okay, so yeah, that's what I was putting some quotation mark, because if you think about it, as said, I'm just speaking about the cardinality of that, which is not that bad. I'm saying that these two things have the same cardinality, but as an algebraist, you probably want more, right? Which you will have soon. That's why I put a quotation mark, because yeah, this is not exactly what we want. We want more. Okay, so we have that, and proposition x1 is a bifunctor. So what is a bifunctor? And here I cheated a bit because I introduced my notation in a way that it's super easy to define a bifunctor. So I will define a bifunctor in a way that you are not used to, and if you are not used to, think about why it's really a good definition for a bifunctor. It can be written in the following way. Xi, first thing, xi composed with the identity, so of course the identity of z, because you composed before, is xi. Identity, or it's also equal to the identity of x composed with xi. So this is a first axiom of bifunctor. And the second axiom of bifunctor is that the following composition, so maybe I will write G2 composed with G1, composed with xi, composed with F1, composed with F2, does not depend on the associativity you choose. Right? This is not exactly the definition you are used to, but think about it, it's the same. You can put your parentheses wherever you want, you will get the same thing. This is the definition of a bifunctor. Remark, Ohm is trivially a bifunctor. Because you already know from, I don't know which grade in junior high school, that you can compose, you can associate as you want composition of map. So just replace in this expression xi by morphism, and you can do that. Okay, so you have a bifunctor, and this is an exercise. I mean, yeah, do it. You will see it's not difficult at all to prove this thing. It takes time. That's why I don't do it on the blackboard. So we have a bifunctor. We have two bifunctors because we have Ohm, so it's also a bifunctor. And then now it's a bit annoying because we have a bifunctor, but it's still only a set. But now I will give you a new exercise. I'm sorry, I'm giving plenty of exercises. I guess I will occupy your evening. So proposition exercise as well. X1 has a natural structure of vector space. X1 of Vx is actually a k-vector space. And I will define the way the operation of k-vector space. So as I don't want to tell you something wrong, I look slightly on my notes. So I take xi and xi prime in X1, Vx. And actually, okay, so first of all, for a k-vector space, you want multiplication with a scalar. So what is the multiplication with a scalar? You define lambda xi, or lambda is in k. You define lambda xi equal just lambda identity of x composed with xi. And if you want, or I encourage you to prove that actually it's also equal to this one. Okay? Okay, so you define lambda xi like that, it's not that difficult. Then you define psi plus psi prime. It's a bit more complicated, psi plus psi prime. What is a good candidate for psi plus psi prime? Well, you want something which stays inside. So what is your first attempt? So let's do the first attempt. I do psi direct sum psi prime. What is psi direct sum psi prime? It's just take term-wise the direct sum. And once you have term-wise the direct sum, you put the map also diagonally. So this is natural way to do. But unfortunately, this thing comes from v square, v plus v, to x plus x. So it's not good. However, you have a trick now, is that you have a natural map from v to v plus v, which is just written like that. So this is a map which goes, so this map goes from v to v plus v. And in the same way, you do the same. Here, you write identity of x, which goes from x plus x to x. And therefore, you went back in your good setting. Okay, I claim that it gives you a structure of vector space over x1. Please do it. Maybe some of you know other definitions of the vector space structure of x1. It is the same, but I decided to stick on that because I'm really interested in extension rather than projective resolution in my talk. So I like this one for now. Okay, so I have that. That's a good question, but for me, both are equivalent. Okay, so this is disclaimer. If you are not used to the language of module categories and things like that, you will not understand what I mean. But saying that can be understood as X1 is a bimodule over the category with the opposite category. But this is exactly the same thing as saying it's a bifunctor. This is a reformulation. In the same way that a functor is a module, a bifunctor is a bimodule. Okay? So if you are used to bifunctor, usually you say that it's covariant in the second variable and contravariant in the first variable, and that the reason that I compose to the left or to the right to make it work without effort. Okay? So I want things to work without reversing a row or whatever like that. I want to have a clean notation. So I compose to the left and to the right in such a way. This is like bimodule. If you do bimodule, left-right bimodule, you put on the left the part which act on the left, and on the right the part which act on the right, so by the opposite intent. Okay, it's the same way. It's the same thing. Okay, finish the disclaimer. I go back to my thing. And some detail is that 0 is actually, but this is a consequence. I mean, this is 0 is equal. So what is 0? There is one canonical choice of extension to put as a 0, which always exists. Of course, you have a vector space, so you have a 0. So you can always do that. So you put y equal x plus z, and of course, you have a canonical way to go, which is to put the identity of x and 0 and the identity of z. Once again, all that does not depend on quivers. So I told you I will speak about representation of quivers, but now I'm mainly speaking about abelian category without saying it. Right? I mean, you can, if you like the abelian category, you can do the same. It does not matter. Okay? And for those who are used to resolution, it even works if you have no resolution. I mean, you can do that. That's also a handy reason to do it. In this case, it does not matter because you have resolution. But, okay. So, okay, this is an exercise. Please do it. I would have said at home, but here in the hotel if you want. What else I wanted to say? Oh, yeah. Something I wanted to say, now it's more like an exercise, but a useful exercise. So I take a short exact sequence. And I call that U and V. And I take F from Z prime to Z. And what I want to say is the following thing, is that, so you can of course compute Xi, so maybe this is the first point, Xi composed with F. And one natural question is, when is it 0? It's 0 if and only if there exists a F prime from Z prime to Y such that F equal V composed with F prime. Okay, so if by doing this operation you find a split sequence, it means that you can factor out through here. This is easy, so I let you have an exercise. And of course you have the dual that I will write a sake of completeness. If you have that, G composed with Xi equal 0 if and only if there exists a G prime, so from Y to X prime with F is such that, not F, G, sorry, G is equal to U G prime. Okay? So you please do it. I mean, please do it. If you are not familiar, please do it. Okay, so now that I have only 8 or 9 minutes, I want to continue this story. And once again, if you have questions, don't hesitate. Okay, and now this equality becomes an isomorphism of vector space. It's why now I could replace it by, okay, if you are, yeah. That's the reason I was a bit unhappy to write equal k before, having said that X1 is a vector space, actually. So it's much stronger. Okay, so now proposition, which, so if you take a short exact sequence Xi, 0, X, Y, V, 0, I will call it UV also, why not? And you take any object U. So I put in rep Q, but once again, it's any abelian category. Oh, no, not completely. Let's stick to rep Q, and I will explain a bit more. There exists what we call a long exact sequence. Of the following form, 0 ohm UX, ohm UY, ohm UV, then X1 UX, X1 UY, X1 UZ, and here I will write in yellow 0, and I will explain you why it's written in yellow in a few seconds. Okay, so I claim I have a long exact sequence. I didn't tell you what is a long exact sequence. A long exact sequence, I will say it orally because it's somehow like short exact sequence. It means that each time you take somebody in the kernel of an arrow, it's in the image of the previous arrow. And more precisely, the kernel of an arrow is equal to the image of the previous arrow. So the kernel of this one is 0. So this is injective in particular, okay? So this is the definition of long exact sequence. And I can tell you how it works. So if you take a certain morphism F here, to whom you want to send it, you have a U, so you have a good candidate, U composed with F. Then if you take another F here, you map it to V composed with F. And then I will go directly here. If you have a Xi here, you map it to U composed with Xi. It's very boring. And then if you have a Xi here, you map it to V composed with Xi. And now you wonder, what should I do here? And actually, you have a good candidate. Suppose that you have a morphism here. So you have a morphism from U to Z. What can you do with that and U to Z? You can pre-compose. So you map, right, I have a morphism from U to Z, so I map it to, I map F to, so psi composed with F. Okay. This is a long exact sequence, so it has all the properties that I said, and it's easy to prove, so please do it. You need to use that to prove. You need the exercise to prove the exactness here and there. For the other one, it's straightforward. Yeah? Yeah, I will say in 1 second. Yeah, sorry. Yeah, okay. People are in a hurry, it seems. You can do in the opposite direction. One thing, I said it's easy. It's actually not true. This one is difficult. So it's not part of the exercise. I ask you to admit. Why is it difficult? Because it actually depends on the fact that I'm speaking about representation of Q. It's not true for every abelian category. Not true in general. It's just for representation of quiver. Okay? It's called what we call an hereditary case. 2, but there are no x2. Yeah, if you are used to x2, there are no x2 because it's a quiver. Oh, yeah. I will do it in 1 second. So you have the dual statement. So the dual statement is I would say reverse the arrow, but it's not completely true, so I will write it. So dual statement. There exists a long exact sequence of the form 0 home VU, 0 home YU, home XU, and then X1 VU, X1 YU, X1 XU, and then 0 that I put in yellow for the same reason as before. So you have a 0. Okay, I really start to miss time, but you have a 0. I ask you to guess all this map because they are as easy as the other to construct. So I'll let you do that. Okay, so now, that's interesting. I have a proof I would like to do, but I'm not sure I have the time to do it. So maybe I will state some result and I will do the proof tomorrow. It might be a good way to state it. Now I want to understand a bit more indecomposable objects. So, right. I will write several statements, but I would like really to spend a bit time tomorrow to say more. So it's a bit separated. I'm kind of jumping to a different topic somehow. So I take an indecomposable object. So I will write it like that. It means just an indecomposable representation of Q. Then, first thing, if F is an endomorphism of X, so you remember an endomorphism means just a morphism from X to X, then there are two choices. F is invertible or F is nilpotent. So here, pay attention. I'm not exactly using that. In representation of Q. It's slightly more general, but it's not all abelian category. So, right. 2. The set of all F such that F nilpotent or F, I will write F nilpotent because it's in context, it's easy, is a maximal ideal of and X. And X is a ring, remember. And actually, I don't want to say that it's a maximal ideal. I want to say that this is the unique maximal ideal. Soon. This is a unique maximal ideal of an X. And this sounds a bit technical, but it's actually very useful. It gives you a corollary that you will like, I hope, if x1 plus x2 plus xn is isomorphic to y1 plus ym, I put a m instead of a n here, with xi and the yi indecomposable, then there exists, so first of all, n equal m, and there exists a permutation such that xi is isomorphic to y sigma I for all I. So this is called Cool-Schmidt property, the kind of unique factorization property. If you have an object which is not indecomposable, it's natural to try to write it as a sum of indecomposable, because at some point you will stop. We are in finite dimension now, so if you try to do that again and again, at some point you cannot anymore, because you have a problem of dimension. And then the question is, but is this process really unique? What tells you that is that it's essentially unique. Okay? I think I will try to give you some ideas of the proof of this thing tomorrow, because it's actually interesting. Thank you very much. Okay. If you cannot read, yeah, I can say there is something which is difficult to read. You can ask me. Don't. It's m equal to n. Sorry, it's this thing equal to that thing. They are the same number of summoned and they are permutation of each other. In other terms, these two direct sums are essentially the same because direct sum commutes. So anyway, yeah, you need to permute them in order to make them equal or isomorphic. So yeah, tomorrow I will prove that. Yeah, I will probably, I don't know.